afternoon, everybody. My name is Isaac Dawson. I am a security researcher at Veracode. Today I'm going to be covering a scalable fingerprinting system I built using Chrome Automation. And I do want to mention real quickly that there's a mistake in my slides. It actually got it down to 15 hours instead of 80. So I'll explain how I got that the performance to be better throughout this talk. A quick word about who I am. I was previously at Stake and Symantec doing application security consulting. I moved to Japan about 12 years ago to help Symantec start up their application security consulting team. And about 6 or 7 years ago, I moved into Veracode into a research role, doing research into our dynamic web application scanner, so automated scanner system. I love Go, I love Postgres and NSQ. Those are the three primary languages and components that make up the system, and I'll explain that today. So a little bit of background. This all started in 2012 when I was really interested in security headers and how developers and websites were using these headers, whether it was content security policy, XXSS protection. So I wrote a scanner to scan this top 1 million list and then looked at the results and saw which ones were configured incorrectly or properly configured. All my scanners use the Alexa top 1 million URL list. It's a list you can download from Alexa. It's a free list. It just contains the URLs and then the ranking. So the first scanner I wrote was called Galexa. It was written in Python and gEvent. gEvent is an asynchronous framework or library you can use with Python. That would write to Kyoto Cabinet, which is a key value store. From there, I would then import into MySQL to do my reporting and analysis. In 2014, I really started to get into Go. So I started converting all my Python into Go. And as a point of reference, the Galexa scanner took about 16 hours to do the top 1 million. The Go scanner took about 2.5 hours. So it was very, very fast, a single instance, just writing directly to a Postgres database. And then in 2016, I started to notice a lot of other security researchers doing very similar analysis of scanning the top 1 million and then providing results on what they saw. So I felt like I needed to differentiate myself. So I wanted to use a real browser. I wanted to see what the browser sees when it goes to these websites and collect not only the top 1 million responses, but also all the sourced in data. So all the image, JavaScript, HTML that was coming in, I wanted to look at those response headers as well as trap that raw data and store it in a database so I could do further analysis using things like Elasticsearch. In July, I started to kind of rewrite everything because I wanted to make it more automated and make it more scalable because I had some serious architectural issues, which I'll cover. So that's where I'm currently at now. So I'm going to jump right into the architecture. I have a lot to cover in a short amount of time. Just to mention, all of these components and systems are running in Amazon AWS Web Services. And there's different types of instances you can choose. There's T-series, which are very cheap, but they use a concept of credits. So if your CPU utilization is below 50%, you won't use credits, you'll gain credits. If it goes over that, you'll lose credits to a point where Amazon will restrict the performance of that particular instance. So you have to be very careful choosing your instance types. The admin service just manages jobs. It's for starting a job, creating the database schema, importing the URL list so the agents can pull from it. The agents, I had about 50 of these running concurrently. They were running C4 large instances, so they're like 3 gigabytes or 4 gigabytes of memory, CPU optimized, so very fast and good for running browsers in. Once these agents finished their analysis, they would store it onto a local queue. The database writers would pull from that, and then they would feed that data either into the database or S3. The database system is running Postgres 9.5. It's a very large machine, M4 X large, so 15 gigabytes of memory, 750 gigabytes of space, enough for me to run my scans with. NSQ is kind of the wiring or the backbone of this entire system. It's a message queue that's very easy to work with. So all these messages that are going between these systems are being sent over NSQ. And then finally, S3 is what I'm using to store the serialized DOM. So when I go to a URL to analyze it, I'll take a snapshot of what the actual DOM looks like at that particular time, as well as capture the raw HTML and JavaScript to store in S3. The message queue, as I mentioned, I'm using NSQ. It's two primary components, NSQD, which is just the message queue that you would publish your messages to or consume from. And then NSQ lookup is more of a discovery service. So all my agents would connect to the NSQ lookup service and say, here's what I provide or here's what I need. And then they could publish and consume on very specific topics or channels. And messaging is just JSON between all these systems. Some helpful features for NSQ. NSQ is also written in Go. This is Go. If people have never seen Go language before. One of my favorite features of NSQ is being able to add the number of handlers. So I can, let's say if I have 6 browsers running, I want to retrieve 6 messages concurrently. So I just bind a function to that, and then I set the number of browsers, and then I get 7 or 6 or 3 messages concurrently. In some cases, depending on network conditions, if I'm trying to communicate with a site, but it's timing out, it's taking a long time, by default, NSQ would requeue my message, which I don't want to happen. If it requeues it, I'm going to have another agent pick it up, and I'll be doing double work. So it's important to use the touch method to say, I'm still working on this, don't requeue it yet. And likewise, if Chrome crashes, I can actually requeue it myself automatically. There's various types of ways you can requeue it. But my favorite feature of NSQ is being able to change the number of messages I'm reading in at any given time. So again, depending on network conditions, I can either start up another worker and start getting another URL to do analysis from, or if Chrome crashes, I can change the in-flight to 0, and I'll stop receiving messages just for that agent. So the normal message queue system will still work. All the other agents will still do their work, but that particular agent would stop reading from the queue. So here's kind of what it looks like from a visual aspect. So the agents, as they come online, they'll talk to the admin server. The writers will all communicate to all the individual agents. And then depending on the type of data, they would either push it to the database or S3. So my system is called Creeper. So I'm going to talk about the actual agents themselves. For those who are not aware, there's a game in the 80s called Creepy Crawlers. All the names like Spider and Arachnid have already been taken, so I just came up with Creeper instead. So some automation requirements that I had. First off, I needed it to be fast. So whatever browser I chose, I wanted it to be very quick in doing my analysis. So that pretty much threw away Internet Explorer and most of Firefox. Another issue is I needed to be able to capture network traffic. So I wanted the raw HTML and JavaScript as it came over into the browser. And this is important because I didn't want to use a proxy. Proxy adds complexity to the system by either making another hop, so there may be caching issues, maybe certain encryption algorithms or ciphers wouldn't be supported. So I didn't want to have to deal with that. And to be honest, if the data is in the browser, I should be able to extract it. I also wanted to capture browser events, so any sort of content security policy violations that were occurring, I wanted to see not only that the security header existed, but how did the content actually work for that particular policy. And then finally, I wanted to inject JavaScript, which most automation libraries support, but I still needed it. So I chose Chrome. Each of my agents runs between 3 and 6 tabs. Again, this all depends on network conditions. As some sites are timing out, I'll dynamically start a new one so I can do additional work. It's running in headless mode, which means that I take the browser, and since I don't have a display, I need to actually render it somewhere. So I use X virtual frame buffer to put the window to do its rendering. I can also get full read access to the network response data, which again is very important. I can easily inject JavaScript and subscribe to console messages. So the agent can be broken down into 4 logical components. The application logic handles processing URLs from the message queue as they come in. I have a concept of a dynamic worker pool. So as I increase or decrease messages, I can increase and decrease my workers. And as those workers start doing work from a URL, they call an analyzer. And the analyzer's process is to load the URL, start capturing network traffic, start capturing the content, injecting JavaScript. But before they do that, they need to borrow a browser. So I have this browser manager that kind of encapsulates everything, where it can lease out browsers and get browsers returned. If Chrome crashes, I have a single point or a single component that I can say, Chrome has crashed, you're not going to be able to do any more work. So after the analysis is finished, it pushes back to the application logic, which then calls the reporter and says, here's the data, and it puts it onto the message queue for DB writers. Now, as for actually controlling the browser, I looked at things like WebDriver, Selenium, which are common automation libraries you can use. The issue with WebDriver is it also uses the remote debugger API of Chrome, but it doesn't give you the low-level access that I required for network response data. So an issue with WebDriver is you can't, or the remote debugger APIs, you can't attach two debuggers to the same tab. So if I use WebDriver, I wouldn't be able to get the low-level access. So the remote debugger API is defined in two JSON files, which is very excellent because it allows you to read these files and then either start looking at the different types of functions or types or events that the API supplies. And when I first started doing this, I was doing it by hand. I'm like, oh, I only need 3 or 4 functions to do my work. And immediately I realized that's not the case because there's all these subtypes and other issues. So I wrote a library called Go Chrome Debugger, which is a wrapper around those JSON files. What I do is I read those JSON files, and then using Go templates, I automatically generate the code necessary for my library to use it. And this is excellent because it gives me remote access to all of the debugger events, functions, and types. If you've ever used the Chrome DevTools, that's all using this same exact API. So anything you can do in DevTools, you can do using this code remotely, controlling it from other code. Another benefit of using templates to automatically generate it is as the protocol files change or as the browser's updated, I can just rerun my code and generate the new API. So anybody who's ever worked with an automated API generation library usually knows they're not really easy to work with. So I wrote another tool on top of my other tool to help me for automation purposes, so trapping the console, injecting JavaScript. I did take some inspiration from WebDriver, so if you've ever used WebDriver, it'll look very similar. A lot of the methods are the same. So let's look at getting CSP events. Very simple, you just subscribe to getting console messages. As these events or violations occur, the CSP handler would be called. I just filter out only interested in security, and then I parse the type of CSP violation. Network responses, on the other hand, are a bit more complicated due to the asynchronous nature of how the Chrome network stack works. So you'll have 3 major functions. You have the request start, response handler, and then response finished. So subscribe to just the last 2. The response handler is called, and this contains a lot of good information such as the request ID, the URL, metadata, headers. The issue is that you can't just read the body because the body does not exist yet. So you have to wait for the response finished handler to be called. So I created a network container where using Go channels and Go routines, I could block this response handler from returning while I waited for it to actually be finished. Once that was called, I would then read the body and then add it to the ready queue saying this response has been finished. Excuse me. So injecting JavaScript, I wanted to not only look at security headers, I also wanted to look at what websites we're using for various well-known JavaScript libraries, and not only the libraries, but the versions of them. So I could do sort of analysis of like how many are vulnerable and how many aren't. If you ever have heard of retire.js and Wappalizer, these are 2 kind of open source tools that you can use that will go to websites and do a very similar thing, but the amount of files that they look for, types that they look for, isn't much. So I kind of combined a little both of those, and I spent about a week just browsing the web, looking in Chromium DevTools, looking at the window object and seeing what was bound to it. In the end, I created about 86 frameworks that I was interested in. One challenge is you need to wait for the page to be fully loaded, and that sounds like an easy thing, but it's really not, and I'll explain that in a bit more detail later. But first I want to look at the queries, or I want to show the queries. So some of these queries are really easy. This is the library that I use. There's 3 properties, the URL, the key, and the statement. The statement is what's actually being injected into the browser window context. And some of them are very easy to get the version information. For example, jQuery, you just do jQuery.fn, jQuery, and it returns a string to you. Other libraries, not so easy. Embedded.js is a good example. It doesn't have any method or property that I can call to get a version string, so I had to do sort of a differential of previous versions. What I came up with is that in Embedded.js 1.0, EJS was bound to the window, and so it was a function, so I could check that type. It also had a function bound to that called EJS buffer. So knowing those two properties, I can say this is version 1. Because versions below 1, while they had EJS bound to the window, they also had an EJS scanner. So knowing these types, and they didn't have an EJS buffer. So using this kind of data, I could determine what version of framework was. And there's other techniques you can use too, such as looking at the number of arguments to a public method. And you need to be careful though, because a lot of these JavaScript libraries are being minified or obfuscated. So you need to look at it from a dynamics standpoint and say, okay, this is kind of the public contract of this library. Even if it's minified, these properties will still exist. So keep that in mind if you're doing any sort of fingerprinting. Injecting is pretty straightforward. Just execute the script. If I get a response, great, add it to my reports. So going back to the challenge of when is a page done? So you might be familiar with DOM content loaded, which is an event that is fired by the browser saying all the tags have been, the sourced in tags values have been injected into the DOM and the content is loaded. However, that doesn't really handle dynamically loaded content, so things using like require.js, which is going to be asynchronously loading in data after the fact. So what I came up with is to listen for DOM change events. So another great benefit of the remote debugger API is I can actually observe how the page is being accessed and modified by the browser or the page. So I can set up these listeners, say, okay, is an HTML element being added or removed? And I listen to this for about 2 seconds. Or excuse me, I listen to this, and if I see no changes for 2 seconds, I consider the page loaded, and then I inject my JavaScript. If it's still changing after this 5-second period, I'll just time out and continue on. A quick side note, when I didn't have this timeout of 5 seconds, I only had a timeout of 2 seconds. What ended up happening is my scan finished in 12 hours instead of 15, but I was missing 600,000 results from my JavaScript libraries. So waiting for the page to be done is extremely important if you want accurate results. Some other challenges. First up was contamination. So what I used to be doing is reusing the same browsers. So I would start capturing, I would load a URL, the document would load, and then I would stop capturing, and then I would use that same browser to turn on capturing again, load the URL. So if I went to Yahoo first, and I captured everything, and then I used the same browser to go to Microsoft, I would see Yahoo's results inside of Microsoft results in my database. So there's some contamination of the data, which is not good. What I ended up doing is to create a pool of browsers. So even though I'm only using 3 to 6 tabs concurrently, I start up 9. And I go through the same process of taking a browser, start capturing, doing all the loading. But now instead of reusing it, I kill it and I add a new browser to my pool, and then I pull another one off from that pool that's sitting there doing nothing. So this not only solved my contamination issue, it increased my performance or how many URLs I could go through, because now I no longer have a page sitting there doing rendering, doing a lot of things while I'm trying to load a new URL. Unfortunately, I found a Chrome bug by doing this. Apparently, if you open and close tabs excessively, you can no longer communicate with the remote debugger API protocol. So I submitted a bug report. I'm sure no one will ever look at it because no one's probably doing this. But I still needed to come up with a solution to it. So what I do is, since I can't communicate with this tab that I just started, I can't close it. So I mark that tab as being dead. And I say, okay, that one I can't communicate with. And then I have a max dead tab count, where if it reaches that, so let's say 3, I'll continue working on my active URLs. I will wait for them to finish, and then I'll kill Chrome and restart it all within my program. Unfortunately, that doesn't always work because there's sites like crashsafari.com. If you're familiar with this site, it was a bug in the history push state where an attacker could recursively add more and more junk onto the navigation history until the browser ran out of memory and then crashed. Unfortunately, this has the side effect of not only killing Chrome, but it also killed my agent. The operating system would just kill everything. So any active tabs I was working on would be killed. While the service would restart, I would lose that active work. And this site cost me about 2 to 3 weeks of development time trying to come up with a solution for it. So I came up with, the first step was to create this package called KillFace, which I use to monitor a process or a series of processes for a certain memory threshold. So let's say if Chrome's taking up more than 60% of the system memory, kill it and then notify me. And that's important because Chrome will crash quite often if you're doing this type of work, but I needed to know it was crashing for this very particular reason, which was out of memory. So then I had this dynamic worker pool where I would reduce the count to 1. I'd say, okay, we're only going to do one URL at a time. I would pause the message queue so it would stop receiving messages so I wouldn't interrupt that. I'd rerun all those active URLs again so I could determine exactly which one was causing the problem and not have any of my other tabs crash. Once that was finished, I would kill Chrome, restart it, and then continue working. Some other challenges, my NSQ messages were too large when I first started this. There's a maximum limit of, I think, 30 megabytes. What I was doing was I was taking all my report data and all the sourced in response, raw response body, putting it into a single message and trying to send it over the queue. That did not work. I tried zipping it, but zipping requires a lot of CPU. It's very CPU intensive. And to give you an idea, I needed my agent to be running at below 25% CPU because the browsers were taking up so much CPU doing software-based rendering that I couldn't afford to have my agent take up resources. Other issues were sites just blocking AWS, the Amazon Web Service IP ranges. This is to protect them from web scrapers, etc. Can't really do much here except for timeout and notify that this site I was unable to connect to. Concurrency issues. This was kind of my first foray into a large distributed system using Go, and I had a lot of resource leaks. And when you're running something this fast for this long, any sort of resource leak is going to cause you trouble either immediately or when you're about 4 hours away from finishing a 40-hour scan, which you don't want to happen. So I had to be very careful. There's a lot of really good tools to help you with these types of conditions in Go. Then finally, site analysis failures, so just not being able to connect or timeout to a site. I have a retry state, so I want to retry 2 or 3 times, and I keep track of that state, which is great because let's say I communicate with a URL, it starts to time out. This is like a 90-second timeout. I know if I retry it again, there's a pretty good probability that that site's going to time out again. So again, going to my dynamic worker pool, I can say, okay, tell the message queue to give me one more message, and I can work on an additional URL. So this increases the amount of URLs I can go through while that one sits there doing nothing. So storing the data. This was, for me personally, this was the hardest part of the system. The first version of Creeper had many problems. First off, RDS did not support Postgres 9.5. 9.5 added a very important feature called upserts, which I'll explain later. So not having that, I had to do many hacks to get my data into the database when I had unique constraints. Duplicate data, since I wasn't able to do upserts, I had to store all the same data over and over again. And to give you an idea, after running a scan of 350,000 URLs, I had 20 gigabytes of Google Analytics JavaScript, 20 gigabytes of Facebook's JavaScript, all the same file, but just stuck in my database. So that wasn't going to work. So what I ended up doing is taking a SHA-1 hash of the contents of the file, using that as the file name, and then I just wrote it to disk, and then I'd import it later. So you can't just store 5 million files in a single directory. Well, you can depending on the file system type, but it's better to put it into subdirectories. So you use this technique called sharding, where you take a unique file name, the first 5 characters, and you split it up into the directory. So you can see here, if this is going to work, the first 5 characters here are the first 5 characters of the subdirectory. And since this is SHA-1, sufficiently random, I get uniform distribution of my files within those directories. Another issue with V1 was I didn't shard my database tables, which means that my tables were really big. And I'm saying 180 million rows for response headers and about 83 million rows for responses. My database tables were normalized, which I'll explain what that is in a moment. Just means that I had these very large tables that I had to do selects from, as well as doing inserts into. So my write throughput was pretty bad. And then finally, I had lock contention, meaning that some of these tables were so big that I couldn't use multiple writers because it would try to write to a table, it would lock it for 5 minutes while I was trying to write to it. I couldn't use another DB writer because it would be blocked. So to import that, all those files, which was about 408 gigabytes of data, it took me about a week to get it imported. So quick refresher for those who are not familiar with database terminology. I'm going to just cover this real quickly. So the top example is a flattened or denormalized table where you have responses and then you have headers and header names. And you can immediately see that the same value is duplicated multiple times. This is fine for relatively small tables, but if you have 72 million rows, this duplication costs you a lot of space. So what you usually do is you'd normalize it, you'd split it out into a header name table, and then you'd use something called a foreign key reference, and then you just use that ID in your response table, looking up the header name ID from that value. Now you need to be careful because it's kind of a trade-off. If you have very unique data, it's usually not worth normalizing. But if you, for example, for header names, I think I only had a total of 22,000 unique header names out of 72 million requests. Header values, however, I had about 525 million. So it didn't make sense to split out header values. It made sense to put that into the response table and split out header names. So write throughput was really important. This, I don't know if you can see, this is the network traffic coming into my 4 database writers. That's about 650 megabytes to 400 megabytes per second to 4 database writers. So about 2 terabytes of data coming in. I need to get this out of my writers as quickly as possible, otherwise they're going to crash. Excuse me. So getting this out was very important, but I also needed to be careful not to overload the database with too many connections. And I also had to reduce lock intention so these writers weren't all trying to write at the same time. So my solution was to, and this is a very common solution by the way, is to batch up these reports and these responses. And then I had a randomized insert of between 2.5 to 3.5 seconds. So the reasoning being if you have 4 writers or multiple writers, they wouldn't all start trying to write at the same time. There would be some sort of a staggering of these writers. This also had the benefit, since I'm only using this insert process once every 2.5 seconds, of reducing the number of database connections. Because I had all this huge amount of data that I could just stuff in one at a time. Here's an example of the batcher code. It's very simple using Go's something called their buffered channels. So it set the max limit, so let's say 1,200. And as the messages were coming in from the message queue, I would add to this report pool. And then that 2.5 seconds, I would call empty it. And the reason that buffered channels are great is because it would, once it fills up, it would lock that message queue from trying to write to it. So I could stop reading messages just by having these buffered channels. Think of it like a blocking queue. So I still needed to get this table and this data in quickly after I took the batch reports. And I used a feature of Postgres called temporary tables. Now, temporary tables are really great because you can have the same exact name for the table, but it only exists in the lifetime of the connection that you made. So I could have 4 writers all using the same table name of header or responses temp, and they wouldn't conflict with each other. They would all be specific to that connection. And I use a statement called copy from, which is a very, very fast, like you can take 1 million records and insert it into a database table under a second, so very quick. The problem is copy from does not have some features that are important to me, namely upserts. So once I created these temporary tables, I would take the batch data, put it in there, and then I would use another feature of Postgres where you can select from a table and then insert that data into another table. So here I would do insert into header names, and then I would select the responses temp header name values, and then insert into the header names table. So that's its final destination. On the bottom, you may notice an on conflict do nothing. This is the upsert. So the benefit of upserts is, let's say I have a header name table with 30,000 header names, and there's one header name that I'm going to be inserting again. So let's say I have this header temp table with 100 headers, but one of them is exactly the same. If I did not have upsert support, what would happen is when I tried to write to that, it would basically have a unique constraint violation, which means that my transaction would fail, and I would not be able to write that other 99 headers that I needed into that table. So by having this on conflict do nothing, it would say, okay, this header name's already there, but you're not going to do anything about it, so just insert the other 99. So upserts are very key for this type of work. Some other challenges, large tables. Doing an insert into select from, while it's fast, it's much faster than just doing multiple inserts. When you do it on a table with 80,000 or 80 million rows, it's going to take a long time. It took between 5 minutes to 10 minutes, depending on my queries. And as these tables got bigger, these DB writers were slowing down. And that's just not scalable. That wasn't going to work if I wanted to not have that whole import process. So the solution is to do sharding. In my case, I chose table sharding as opposed to database sharding. Table sharding is much like I explained with the file system sharding earlier, where you break it up into different segments. It requires a key for tables. In my case, I'm lucky because the Alexa list has the URL ID or the ranking. So I use that as my key for all references to all the data that's going into the database. Now, you only really need to do sharding for very large tables. So you don't need to do this if you have below like 10 million tables, or excuse me, 10 million rows. So here's an example of just not having table sharding. You just take your data, you do the insert into, it goes into the same table, that's great. And when you have sharding, you have to use kind of a mathematical operation called the modulus. You take the modulus of the number of times you want to shard it, that would create your shard key, which, since you have that input ID in the database table, you always have this reference to it. So you always can reproduce that shard key given the input ID. And then it just splits it up, and then depending on the shard key, it goes to the correct table. So creating a shard key is very easy. You just need to have some sort of key or identifier, in my case, the input ID, and then the number of times that you want to shard it. So in my case, I did 32 times, so I created 32 of these job response tables. The key would be part of that table name, where I had functions which allowed me to use the job name plus the shard key and those temporary tables, so I could immediately know which table, final destination table, the sharded data would go to. So very helpful to that. Now, there are some downsides with sharding. First off is complexity for querying. Doing any sort of select statements on 32 tables is not fun. What I ended up doing is just creating a new table and extracting particular data I was interested in, namely security headers. In the future, I may move to Citus, which is a sharding technology that uses Postgres extensions. So you would have a master database server, you would install the extension, and then it would automatically determine how many sub-databases to go to. So you could start up 5 databases behind that, and then it would just automatically route to the particular database. So probably as I scale this up even more, introduce crawling, introduce other things, I'm probably going to move to Citus. Response data, I first started trying to insert this directly into the database. This is an example of it crashing. Around 1,800 hours, you can start to see it climb up. This is bad. This is really bad. Around 1,800 hours, I realized that this thing was probably going to crash, but I wanted to see what happened, so I let it run. And then around 2,100 hours, it dips down to 20% because all the agents behind it crashed. What happens is the database writers' queues filled up. That blocked them from reading from the queue from the agents. The agents' queues filled up their disk, they shut down, and yeah, that's why it crashed. So I gave up trying to put it into the database. I'm like, you know what, I'm just going to put this in S3. S3 is a kind of like a key value store that you can use from Amazon. They limit you to 100 requests per second by default, but in my case, I'm pushing between 200 and 2,000 requests per second, because again, I have 4 database writers. They're all trying to insert data into S3. I had to contact their support. It took 2 or 3 days of emails back and forth. They're very concerned with how you are generating your key names, because just like the file sharding, they don't want to have, they need to have uniformly distributed key names. So you need to make sure that you code that in properly. You also need to implement an exponential backoff, meaning that if the request to S3 fails, you retry again, but you sleep for a little bit, and then you retry again, you sleep a little bit longer. And I retried about 10 times. But just to give you an idea, I only had about 7 errors the entire time I was running for a 15-hour scan. So it's a very scalable system, and I definitely recommend it. So that SHA-1 hash key name is also stored in my database. So I would have a reference to it so I can look it up later when I go to import it into S3. One thing I do want to mention is it definitely makes sense to use the head object, which is basically seeing if the object exists or not without actually getting the response of it before you do a put object, actually storing the data. Head objects are significantly cheaper. Here's an example. I don't know if you can read this in the back, but it cost me about $30 US doing 6 million requests of putting files. And it only cost me $7 for doing 18 million requests for checking if they existed already. So absolutely recommend checking if they exist first. And then finally, used some more Postgres-related features, created unlogged tables. Unlogged tables will basically disable their crash recovery system. So there's something called the write-ahead log, which will take snapshots for crash recovery purposes. In my case, I don't really care if my database crashes because I can just run a new scan. I don't have like financial transaction information I care about, so unlogged tables are a great choice because it does help performance significantly. All the Postgres configurations that I modified were pretty much all centered around this write-ahead log, trying to disable it or make it take longer than it normally would. Disabled fsync, which basically is used for storing that to disk. I didn't care about it, so I disabled that, etc. Right, so let's move into some of the results. First, I want to look at the scan statistics. I had a total of about 72 million responses, 525 million headers to review, and this is after filtering common headers like connection, date. Before I wasn't filtering that, and I had about 802 million rows, so I immediately removed 300 million rows just by filtering out certain headers. I had about 2 million JavaScript libraries and version results, 67,000 URLs I could not communicate with. What I found interesting is almost 15% of the top 1 million will automatically redirect you to HTTPS, which is great. So 145,000 of that. URLs with CSP violations was about 740. Scan time, 15 hours. And the cost was about $343 or like somewhere around there. For CSP violations, so you may notice I said 740 earlier. It's actually 722 unique final URLs because the Alexa list is the first URL you go to, but it's going to redirect you, and I follow those redirects to the final page. So out of about 5,000 sites, 722 of those had violations. Some of them are security sites like Global Sign, which does trust and certificates. And unfortunately, even my own company's website's on this list, which they tell me they're working on, but who knows. Well-known organizations, Alibaba, DoubleClick by Google, even Mozilla, which basically created CSP, has violations on their sites as well. Taking a look at some of the violation types, ScriptSource by far has the most violations. Since this is a sum, I need to mention that one site in particular had 200 ScriptSource violations, so keep that in mind while you're reading this graph. Image source, frame source, font source, all relatively the same. Style and connect didn't have too many, and then the rest were little to none. JavaScript libraries that had more than 3,000 results. If you can't read that in the back, it says jQuery. That had about 720,000 sites running jQuery. Next in line was jQuery UI with almost 200 million. So almost everything is basically running jQuery out there still. Sort of next generation frameworks. Backbone.js had almost 18,000 results, which I found surprising. Angularjs came in second with 13,500. I do need to mention though, I did not realize Angular 2 changed the way that you get version information. Before it was like angularjs.version, you'd inject that, you get the version string. Now it's like core.version and you get the Angular 2 version. So the next time I run this, I'll include that as well. React.js was relatively low. I was kind of surprised. Barely 3,000, maybe 3,200 or something. One point I also want to mention is that this is only looking at the final top page of a URL. So if I crawled into it, looked at the login page or the registration page, I might get different results. And that's actually something that I should mention I plan on doing. So vulnerabilities, I need to also take a side note here. I created a JavaScript version string parser where I'd parse out the major dot minor dot revision and then sort of beta and RC. And I needed to do this because vulnerability reports are very vague. If you look at CVEs for cross-site scripting bugs for jQuery, it'll say versions 1.2 through 1.6.8 RC1. So I needed a way to parse those strings and then do a range or match comparison or an exact match. So in the end, I created a database of vulnerabilities of about 64 different vulnerabilities. And of course, jQuery had the most because it's running on the most websites. Angularjs came in fourth. These are all Angular expression sandbox bypasses. Although now I've heard that Angularjs will be removing the expression sandbox, so who knows, we may have more issues with sites running Angular. Now looking at some kind of ridiculous data. This is the longest security header award. This is a content security policy for insightguides.com. It looks like it was copied and pasted like 20 times. I don't know what they're doing. Some of my favorite HTTP status lines, so HTTP response protocols like HTTP 200 OK. In this case, it's 500 access denied with a full file system path. I saw many status lines with raw SQL errors, and then funny messages like server made a big boo. But my absolute favorite one was no hacking. I saw that when I was going through my data. I was like, okay. So to wrap things up, if you're looking for a message queue system and you don't want to deal with like RabbitMQ and all the nightmares of working with that complex beast, definitely look at NSQ. Concurrency can absolutely be difficult, especially when you're trying to synchronize the data for writing, but just stick with it. If you're doing lots of little inserts, I highly recommend batching everything up and doing inserts one at a time. If you have database rows greater than a few million, look at sharding if you need to. Obviously, look at your performance and determine that way. And absolutely test different types of table schema, whether you're going to normalize certain things or denormalize other things. You really got to play around with large data sets to see what your performance will be like. And finally, treat browsers like garbage. They will have bugs, they will crash, and you really, from your code, need to handle those conditions. If you don't, your system just won't work. So that pretty much wraps it up. I just want to give thanks to CodeBlue, translators, interpreters, and all my coworkers for listening to my rants every day. And I guess we'll open up the questions.